Solar controllers. There is more than one type of solar controller technology out there. The two main players on the solar controller market, as of 2023, are PWM, Pulse Width Modulation, and MPPT, Maximum Power Point Tracking. I'm not going to cover how these technologies actually work, as that's not particularly important for the scope of this tutorial. However, I will explain their features, their differences, and their pros and cons. In short, the PWM, Pulse Width Modulation, is the older, more mature, and nowadays significantly cheaper solar controller technology that has been of late in many ways superseded by the more advanced, more costly MPPT, Maximum Power Point Tracking technology. However, you can still acquire PWM controllers at usually very reasonable prices. If you are buying a solar controller for the first time, be sure to know whether it is PWM or MPPT. So what are the differences other than the costs? In short, the MPPT is more efficient and more capable than the PWM solar controller, and generally safer. How much more efficient is MPPT over PWM? Well, it's reckoned that the MPPT solar controller gives anywhere from 5 to 25% more efficiency over the PWM solar controller. The MPPT technology has a greater ability to turn sunlight into battery charging electricity. But that doesn't mean that the PWM solar controller is necessarily a lesser piece of equipment. It's just different, and maybe a little more limited in the scope of the ways that you might use it. It's up to you, really, if you feel that the promised 5 to 25% increase in efficiency from the MPPT solar controller justifies the several %100% increase in price, then that's the route you might take. My personal view is, if you're only planning on using a small solar panel wattage system and are not going to be putting any large demands on your DC electric requirements, just like charging a phone or two or a laptop on weekends in the summer months, then a PWM solar controller is probably all you need. However, if you feel you're going to need more electric power throughout the year and through the darker winter months, then I would suggest seriously considering an MPPT solar controller. How important to you are your solar power needs? Are you going to need to try and squeeze every watt of electrical power out of your solar panels? Do you live in low sunlight areas where there is little to low solar irradiance? Irradiance means sunlight. Will you need to acquire your electric power solely from your solar panels? What we need to take into account is, if you are in some way reliant on what solar power you can harvest, then I would suggest pay the extra for an MPPT solar controller. If you're not so reliant on generating electric power solely via your solar setup, either because you don't absolutely need on-demand electric power at all times, or you are set up to acquire electric power using alternative methods, like electric power generated from the running of a combustion engine DC alternator, using a DC to DC charger or a split charge system, or your power comes from an AC electric hookup to a domestic power grid to charge up your leisure battery or leisure battery bank. You clearly are not that reliant on solar power. A cheaper PWM solar controller might be a realistic consideration. However, if having electricity available to you is of some importance regardless of the environment and the limits of possible alternative sources of electrical power, then an MPPT solar controller might be the better choice, even if it does cost more, as the initial expense will be outweighed by its efficiency in electrical production over time. Choosing a solar controller, it's up to you which solar controller route you choose, be it the PWM or MPPT controller, basing your choice on how much your budget is and how much in the way of electricity you envisage yourself trying to create in the way of solar energy harnessed and converted into electricity by the sun or via your solar panels. You're going to have to calculate the power that your solar panels might generate at the maximum of their ability, and also take into account if you might be considering adding more panels in the future, hence future-proofing your system, in order for you to gauge what amperage of solar controller to acquire. It's not a problem getting a higher amperage wattage rated solar controller than you have solar panels to generate electricity for. You can always add more solar panels later. However, the limiting factor is more likely to be how much electricity or amperage, to be specific, that your battery or battery bank can handle having sent to it. Some of the technical aspects of the PWM solar controller that differ from the MPPT controller that could sway your choice one way or other might be 1. A PWM solar controller has problems limiting the amount of amperage or current it can pass through its circuitry. Let's imagine you had 400 watts of solar panel generating, let's say, 24 amps at 17 volts, and a PWM controller rated at just 20 amps. Then, if the sun got bright enough to max the panel out and create the 400 watts, you could burn out your PWM solar controller, which clearly would be a fire hazard, because the PWM controller was rated at just 20 amps. However, your solar panel created 24 amps. That's a 4 amp overload. This issue could be remedied with the correct amp rated or higher amp rated PWM solar controller. You should always use a PWM solar controller that is rated at the very least 1.25 multiplication rule than the amperage handling ability, or IMP, amps maximum power, of the solar panel or solar panel array. Again, taking our earlier example into account using a solar panel or solar panel array, we would calculate the solar panel's maximum amperage output, or its IMP, amps maximum power, like in the earlier example of 24 amps, and multiply that amperage by 1.25. Hence, 24 times 1.25 equals 30. If you can't do the sum in your head, then simply use a calculator. So a 30 amp PWM solar controller, at the very least, would be the safest to use with the 400 watt solar panel or solar panel array. This again is just an example, so please don't use these specific figures for your solar controller and solar panel evaluation. However, do use the 1.25 multiplication rule. An example, again using a PWM solar controller, would be a 100 watt solar panel. When receiving maximum sunlight, apparently, according to its documentation, creates 6 amps IMP, amps maximum power, at 17 volts. The PWM solar controller can trim the voltage down to the required battery charging level, and that voltage may be adjusted by some kind of programming interface built into the device. However, the amps or current can't be adjusted on PWM controllers. The 6 aforementioned amps, or IMP, amps maximum power, should be multiplied by the 1.25 multiplication rule. Hence, 6 times 1.25 equals 7.5 amps. So the very minimum amperage handling ability of the PWM solar controller you would want to acquire for the example 100 watt solar panel would be a PWM solar controller of 7.5 amps or above, probably around about a 10 amp model. Number 2. An issue with PWM controllers is their lack of ability to control the amount of amperage or current that can pass through their circuitry. They can control voltage, but not the amps or current. Let's say you had a leisure battery that gets hot as soon as you push more than 18 amps charging power at it. Please check out my battery basics tutorials to find out more about battery charging and discharging factors. So you might need to limit the amperage current that is generated by the solar panels and is being sent from the solar controller to the leisure battery. This is something a PWM solar controller will struggle to do, regardless of its stated amperage rate, that being what the PWM unit can handle coming into it from the solar panels. The physical solar controller is more likely to melt down or go up in flames than it is to reduce overcurrent being sent to the leisure battery. The only thing you can do in the PWM solar controller is to reduce the amount of your solar panels, or solar panel generated electric wattage, or the physical size of your solar panels or solar panel array, in order to reduce the solar panel's overall generated amperage. So finding the balance between maximum solar power created, VMP, volts maximum power, and IMP, amps maximum power, to the amount of electricity your leisure battery can handle without getting overheated is of tantamount importance in a PWM system. You might find that lead-acid batteries are somewhat more forgiving than lithium-ion LiFePO4 batteries, but you should still be sure to check all the wiring and connections and batteries for excessive heat when your solar panel system is creating its maximum power. Anything more than lukewarm will over time deteriorate your battery power system. Number 3. A third thing PWM controller cannot do is convert excess voltage generated by the solar panel into amperage current, as an MPPT solar controller can do. Again, using the earlier 400 watt solar panel example, generating 24 amps at 17 volts, an MPPT controller will convert the 17 volts voltage down to a usable voltage that is better for charging your leisure battery, like maybe 13.6 volts, depending on what kind of battery you're trying to charge, and then turn the excess 3.4 volts into amperage. In short, PWM controllers are okay with lead-acid batteries if they create a little more amperage than needed, but not so good with lithium LiFePO4 batteries in respects to heat buildup at the battery and all associated connections and wiring. Now, an MPPT controller, again using a 400 watt solar panel as an example, generating let's say 24 amps at 17 volts. However, we are using the MPPT solar controller rated at just 20 amps. If the sunlight is at its maximum and the solar panel is creating 400 watts or 24 amps at 17 volts, then the MPPT controller will regulate and pull down the amperage to the desired 20 amps or less, as an MPPT controller will compute and monitor the leisure battery's voltage needs and will also limit the amperage to the best rate to charge the battery, regardless of the battery's chemistry, using the most ideal charging formula or profile for the specified battery. Any excess power that cannot be sent to the battery will be safely controlled and discharged by the MPPT controller, usually in the way of moderate heat discharged through a metal heatsink built into the body of the MPPT controller, or by a fan built into the controller, discharging generated heat. Or the excess power might be channeled to a couple of screw-down wire terminals that you can connect something to, like a light bulb or a fan, to burn off any excess electricity generated by the solar panels that cannot be stored in the battery, maybe because the battery is full. Another scenario that is handled by an MPPT controller is, again, we'll use the 400 watt solar panel as an example that might generate up to 24 amps at 17 volts under ideal sunny conditions. However, in this example, the sunlight conditions are not ideal. The sky is a little overcast and cloudy. The panel is not generating its claimed maximum power of 400 watts, it's only generating half of its stated maximum wattage due to the poor sunlight. In this scenario, it's only creating 200 watts due to poor light conditions. Most solar panels will pretty much always generate their stated voltage, even if the light is not so strong, that being 14 volts VMP, volts maximum power, as in our example. However, due to the poor light, the solar panel will only be generating 12 amps instead of the earlier 24 amps at 17 volts VMP, volts maximum power, being sent to the solar controller device. Here lies another one of the features that puts the MPPT solar controller over and above the PWM solar controller. The 3.4 volts of excess voltage over and above the 13.6 volts required to charge the leisure battery will be converted into amps, so nothing is wasted. You will actually send something more like 14 amps at 13.6 volts to the leisure battery, again because the 3.4 volts of excess voltage that was being generated by the solar panels has been turned into amperage. So the leisure battery or bank of leisure batteries are getting the ideal voltage level to charge them up and the ideal volume of electric amperage current flow to also charge them up. If you need to understand a little more about watts, amps and volts, then please watch my earlier number 3 DC Electric Basics tutorial. Please note, none of these figures are exact, as different solar panels and different solar controllers work at different rates, as do different leisure battery chemistries require different voltages to best charge them. However, this should give you an idea as to the differences between the cheaper PWM solar controller and the more expensive MPPT controller, and as to how MPPT controller is more efficient than the PWM solar controller. In regards to understanding solar panels and their wiring, please watch my number 9 Solar Panel Basics tutorial. Although I've mentioned solar panel wattage as a measurement factor for the solar controller that you might want to acquire, amperage might be the more common measurement when it comes down to how solar controllers are rated. They tend to be sold on their amperage rating handling ability, not their wattage. In short, the amperage factor of a PWM solar controller is not regulated. This can be an important issue. A PWM solar controller will simply burn out. This is obviously a fire hazard if it is sent too much power from the solar panel or panels it is connected to. You should only ever connect the correct rated or higher rated PWM solar controller with the stipulated amount of IMP, amperage maximum power, being generated by the attached solar panels. Remember to add the earlier 1.25 sum to your IMP, amperage maximum power also. PWM solar controller controllers will control the voltage levels sent to the battery or batteries from the PWM solar controller's VMP voltage maximum power, but not the amperage IMP, amps maximum power. Not overdoing the amperage current IMP being sent to a PWM solar controller is tantamount important. You need to rate your PWM solar controller correctly to match your solar panel or panel's maximum power output. Another issue with PWM solar controllers is they don't convert excess voltage into amperage current as MPPT controllers do. So on the whole, as I said earlier, MPPT controllers are significantly more flexible and efficient than PWM controllers. The amperage factor of an MPPT solar controller is regulated and limited to the MPPT solar controller's rated amperage limitations. That meaning an MPPT solar controller that is stated as a 20 amp solar controller will never pass on more than 20 amps to the leisure battery. A 30 amp MPPT controller will never pass on more than 30 amps to the leisure battery. If the solar panel or array of solar panels should generate more amperage maximum power, or IMP, at the VMP, voltage maximum power, then the MPPT controller will limit that IMP amperage maximum power to the MPPT solar controller's factory stated rate. Sometimes via software you can lessen the amperage rate of your MPPT solar controller. Hence, if you had a 30 amp MPPT solar controller, you might be able to, via its software, reduce its rate from 30 down to, let's say, 18. This is often possible with some brands of MPPT solar controller. Basically, an MPPT solar controller can control and regulate both the IMP, amperage maximum power, and the VMP, voltage maximum power, that a solar panel or array or solar panel generate in the way of battery charging electricity. However, a PWM solar controller will only control and regulate the VMP, or voltage maximum power, that is used to charge your battery or battery bank. It cannot control the IMP, amperage maximum power. Lead-acid batteries might be a little more tolerant of over-amperage. However, LiFePO4 lithium-ion batteries can be more sensitive and heat up if the amp rate sent to them is too high. Please see my tutorial on lithium-ion batteries and their basic C rates. C rate might stand for charge or discharge rates. The letter C is often used to indicate what the charge or discharge rate of a battery is in the lithium phosphate 4 battery world. I have found in my system that any more than 18 amps sent to my lithium-ion leisure battery will start to heat up the battery cells and connections. That is why I have limited my MPPT solar controller to just 18 amps. However, my solar panel array is 4 times 100 watt panels, generating in maximum ideal sunlight up to 24 amps, IMP, amps maximum power, at 17 volts, VMP, volts maximum power. I personally am charging up a 100 amp lithium ion battery at a 14.4 volt charge, so my MPPT solar controller will use the excess from the 17 volts sent from the solar panels to the MPPT controller. 17 minus 14.4 gives 2.6 volts excess, and converts the excess 2.6 volts into amps, and then add those amps, if needed, onto the amperage current, being that it is sent to the battery in order to charge it. Hence the amperage is being made up from the excess voltage, even in lower lighting conditions, on the whole more efficient. Let me correct this. My MPPT controller is actually rated at 20 amps. However, via the software, you just log in via your phone, which I'll explain in a bit, I've reduced that 20 amps down to 18 amps. As I might have mentioned earlier, you could have a 30 amp MPPT solar controller, and you could potentially, certainly on the ones that allow software changes, some of them have hardware changes also, where you can just move a pin. However, on mine, I was able to reduce it from 20 amps down to 18 amps maximum. Now, as I've explained, my MPPT controller is rated at 18 amps. Well, as I said earlier, 20, but it's been reduced down to 18. So the controller, out of the 24 amps that my solar panels could potentially generate, if it had maximum ideal sunlight, will only send 18 amps to the leisure battery, as the MPPT controller regulates or limits the amperage current being sent to the battery or batteries, keeping the excess 6 amps to be dissipated through its heatsink or burned off via a controlled and safe method. Some MPPT solar controllers have extra screw-down terminals that allow you to use this excess solar generated electricity in an alternative way. I usually wire these load terminals up to some interior fans in my cabin camper van. The excess solar power generated electricity is burned off by cooling the interior of the van with DC electric fans. However, these, sometimes termed as load screw-down terminals on my MPPT solar controller, can be used for any number of electrical power applications, as long as you are aware that they will only generate electricity when your solar panels are being maxed out, or your battery bank is full, and your MPPT solar controller is looking for ways to dump excess electricity. Some low-voltage DC refrigerators can also facilitate the use of this excess electricity by having special wiring terminals or a plug that you might connect to the solar controller's excess load. The reason I'm using more solar panels than my MPPT solar controller is rated for is I spend some time in the northern hemisphere where sunlight is not as voluminous as in the closer to the equator regions, so my solar panels are not as maxed out. I need to harvest as much sunlight as I possibly can under lower sunlight conditions. Hence, I have more panels than I might need if I were, say, located in a sunnier region. However, should it get sunny, I am safe in the knowledge that my MPPT solar controller can manage the slight excess in power generated by my solar panels. Solar panels can be wired up in different ways, that being in parallel or series, or a mixture of parallel and series. All these different solar panel configurations giving different voltage and amperage outputs, yet given the same wattage. This is explained in more detail in my number 9 solar panel basics tutorial. So please watch and listen to the number 9 solar panel basics tutorial to get an idea of what the total amperage being generated by the solar panel or solar panels array is, or might be, before deciding on what solar controller to acquire. Don't be taken advantage of by a salesman. Knowledge is also power. So I am again going to use an example scenario to help us with the solar controller tutorial. I'm going to use a total of 4 100-watt solar panels that are wired up in parallel on a camper van roof totaling 400 watts. How the solar panels are wired up to one another is very important consideration, that being how they are combined, be it parallel wiring or series wiring or a mixture of both parallel and series wiring. Again, see my number 9 solar panel basics tutorial. You might also use the figures given from my earlier combination of panels, like they represent a single panel. Remember, all my examples are just that, rough examples, just used to aid in describing how a solar controller works. None of my numbers should be used specifically. In short, most decent solar panels are usually supplied with a label stuck on the back of the solar panel, which will have pertinent manufacturer's information that we are going to need. If you can't find this information, then please see my number 9 solar panel basics tutorial. Actually, see my number 9 solar basics tutorial regardless of whether this label is on the panels or not. The manufacturer's supplied information on the solar panels will give a maximum current amperage in electric flow called the IM or IMP, which stands for amperage maximum power, that might be produced under ideal sunny conditions by the solar panel. The IMP is the important consideration for our solar controller. The label will also give an ISC, amperage short circuit. This is more for testing purposes and is not that important for our solar panel or solar controller calculation. I explain in more detail how ISC, amperage short circuit, and VOC, voltage open circuit, are used for solar panel testing in my number 9 solar panels basic tutorial. The solar panel supplied information will also give the nominal voltage created by a single panel, represented by the letters VM, voltage maximum. Don't get confused by the voltage created by the panels, as it will probably be higher than 12 volts, usually anywhere from 18 volts to 22 volts and sometimes even higher. The panels don't need much in the way of sunlight to create the VM, voltage maximum, but they do need the maximum level of sunlight to create the IM or IMP, amperage maximum or amperage maximum power. Volts timed by or multiplied by amps will give the watts figure. Please see my number 3 DC Electrics basic tutorial. Please note that the letter I in electronics stands for current or amperage. Yeah, it's weird, I know, but it is what it is. Please see my tutorial number 3 DC Electric Basics to get a little understanding of the relationship between volts, amps and watts. It really isn't that difficult to grasp once clearly explained. So, what do we need to know about wiring up and installing solar controllers? They're really not that complicated to wire up. Usually, they will have 2 screw down terminals on the solar controller for the positive and negative cable wires that should be connected to the solar or PV, photovoltaic panels. Important, these cable wires both positive and negative, should be run directly from the solar panels to the solar controller, and at no point should the conductor or the metal aspect of those wires touch anything else, like vehicle metal bodywork or other wires. The negative ground earth of this connection, that being between the solar panel and the solar controller, is unique and exclusive to the relationship between the solar panel and the solar controller. So the positive wire from the solar panels goes directly to the positive terminal of the solar controller, and the negative cable wire from the solar panel or panels goes directly to the negative terminal of the solar controller. It's okay if the cable wire's sheathing or the wire's insulation should touch the bodywork or other cables or wires, but not the metal part, the conductor. There will be two screwed down terminals on the solar controller, positive and negative, that should be connected to the leisure battery, usually marked BAT or battery. It is possible to connect the solar controller negative directly to the battery negative, or possibly to the bodywork of your vehicle, if that is, your vehicle has shared earth-ground negative metal body, often termed as earth-grounded or negative-grounded vehicle, which isn't all that unusual. Please see my number 3 DC Electric Basics tutorial for more information on earth-grounded bodywork. Important: always connect the leisure battery cable wires to the solar controller before connecting the solar cable wires, as there might be a little surge of power from the solar panels into the solar controller and it will have nowhere to go if you have not first connected your leisure battery. This surge of solar electricity could damage your solar controller. So again, be sure to connect the battery wires to your solar controller before you connect the solar panel wires, or do it in the evening, or do it with your solar panels covered with a blanket. But you really need to wire up the battery aspect of your solar controller before you wire up the solar control aspect. There might be two other screw down terminals sometimes called load, that are used for dumping excess power generated by your solar panels. If the leisure battery is fully charged, the solar panels might still be generating power, so the MPPT solar controller might need to dump or get rid of that power somewhere. Most MPPT solar controllers will either burn off that excess power in a controlled way using a heatsink that usually looks like metal fins on the MPPT device. The MPPT shouldn't ever get overly hot, although MPPT controllers can handle some excess amperage and will warm up a little. That's okay. However, it's still best to get an MPPT controller that is rated pretty close to your solar panel output, if not higher. If you're using a PWM solar controller, it is very important that it be rated at a higher amperage than your solar panel's total amperage output, as PWM solar controller doesn't handle heat very well and can be a fire hazard. Although MPPT solar controllers can handle some excess amperage, it's still always best to get an MPPT solar controller that is rated pretty close to your solar panel maximum output, if not a little higher. Extra remote switch screw down terminals are often just for a solar controller on-off switch extension. These terminals might be cable wired up to a lithium-ion LiFePO4 battery's BMS device. The BMS will relay to the solar controller via these terminals that the lithium-ion LiFePO4 battery is full, or there is a problem, and stop the solar controller from passing any more electricity to the lithium-ion battery, effectively by isolating the solar panels from the solar controller. You don't have to use these remote switch terminals if you don't really need to control switching the solar controller on and off. You could always put your own manual on-off switch on this circuit if you wish to manually and physically control the solar panel's on-off status. There might be a couple of additional screw-down terminals for leisure battery heat sensor wires, and there might be a plug or something for device communications with other related LCD real-time monitoring panel devices. Please read the manufacturer's instructions as to how these might be used. You may have to attach a computer to program your solar controller for the type of leisure battery that it's going to be connected to. Some solar controllers have little switches or bridge jumpers that allow you to configure them, and for your leisure battery type, an ideal voltage to charge your attached batteries at. This, again, should be in the solar controller manufacturer's included documentation. Please read carefully. It shouldn't be all that difficult to figure out. Now you have something of an understanding of the basics of solar controllers. Some solar controllers have the ability to log into them via a Bluetooth application on your phone that will allow you to program them and monitor and log the power being generated by your solar system. Please see some of my solar controller product reviews. Keep in mind that regular 12-volt nominal lead-acid batteries usually will accept a voltage charge of between 12 volts and 14.1 13.1 volts. That lead-acid battery is fully charged when after a 1 hour resting period, that is, not being charged or discharged, it holds a stable 12.6 to 12.7 volts. Lithium-ion batteries will accept a charge of between 12 volts to 14.4 volts. A 12-volt lithium-ion battery is fully charged when after a 1 hour period of resting, that is, not being charged or used or discharged, then it holds a stable 13.4 volts or higher. Just multiply these figures if your nominal battery voltage system is rated at a higher voltage like 12, 24 or 48 volts. I think that pretty much covers all the basics of solar charge controller systems. It is suggested that you locate your solar controller close to your leisure battery or battery bank, which is a good suggestion. However, if it is not possible to locate your solar controller close to the leisure battery or battery bank, then be sure to use the appropriate gauge, that is thickness, of wiring. Taking into account if you use any extended lengths of wiring, you need to use a heavier, thicker conductor, that being the metal part of the wire, when using longer lengths of wire. Due to what is called resistance in the wire, due to its length, it needs more meat to compensate. If you can, after figuring out how long a piece of cable wire you are going to use, connect the positive end of this cable wire to your leisure battery and the negative wire if you're using a negative from the battery. Maybe you're using an earth-grounded vehicle, so the metal bodywork of the vehicle serves as a negative connection. Don't touch these wires together or you'll get a big spark. Then check the voltage of what will be the solar controller end of the cable wire with a voltmeter, if you have one or can borrow one. Then check the voltage at the battery end. They should match and be exactly the same voltage at the solar controller end. If not, your cable wire is too thin, or if it's a very, very small amount of voltage drop, you might have to compensate for the drop by programming in a slightly higher voltage into your solar controller, if it's possible to compensate for the slight drop in voltage due to having a wire gauge or length that isn't best suited. Probably best just to get a heavier gauge of wire. Please see my tutorial on number 5 electric wiring. Don't forget to use fuses or circuit breakers rated at the same rate as the solar panel controller on both the solar panel side and the battery side. Some solar controllers can accommodate a built-in fuse and come with a fuse rated at the same rate or a fraction above the solar controller's rated amperage. This fuse, more often than not, is related to the leisure battery side of the solar controller circuitry, so you should always put a fuse or circuit breaker on the solar panel side of the circuit between the solar panel and the solar controller. I like to use a circuit breaker rated at the maximum IMP of my solar panel or calculated combined maximum amperage rate of my solar panel array, taking into account the method used for wiring the solar panels. Please see my tutorial number 9 on solar panel basics. Then I'm sorry, but I seem to have forgotten something rather significant. That something being the limitations of a solar charge controller's maximum voltage handling ability. I'll quickly point out that most all PWM solar charge controllers have a maximum voltage input, that being from their prospective solar panel connection, to be around 50 to 60 volts maximum, regardless of their amperage to leisure battery rating. An MPPT solar charge controller's voltage and amperage that may be sent to a leisure battery are normally limited and controlled by some way of configuring the MPPT solar charge controller, be it via a software programmable interface or via some hardware jumpers or external switches. However, the amperage and voltage that come from the solar panel or panels that is being sent to the solar charge controller has to be thought through and designed in such a way that the solar charge controller can handle the amperage and voltage, and you get an ideal balance between input from the solar panels to the solar charge controller and output from the solar charge controller to the leisure battery or banker batteries. This balance should take into account bright and sunny days and not so sunny days by getting the optimal power from whatever sunlight is available without causing your solar panels, solar charge controller or leisure battery any extreme difficulties. I'll give you an example. My solar charge controller is indicated to be rated at 20/100. That means it can send a maximum of up to 20 amps to my leisure battery if the battery is a 12-volt nominal battery. If, however, the leisure battery or banker batteries work at a higher voltage, then you should read the solar charge controller's technical specification sheet. The 100 figure given in the description applies to how much voltage the solar charge controller can handle coming into it from the solar panels. This is important, and I will explain this factor in more detail in my number 9 solar panel basics tutorial on how to craft and manipulate the amperage and voltage coming from your solar panels and being sent to your solar controller in the most efficient and balanced way, so as to get the optimal efficiency from your solar setup. So just keep in mind that an MPPT solar charge controller is usually rated at the maximum amperage that it will send to the leisure battery, and it is also rated at the maximum amount of voltage it can handle coming from the solar panels. A PWM solar charge controller is rated at how much amperage it can handle coming from the solar panels and being passed through to the leisure battery. Please like and subscribe for more off-grid information and tutorials.